Okay, Unit 3, Lesson 2. Welcome back, guys. This is our third to last lesson, so there's going to be two more left after this. And so, let's see. This one is over confidence intervals, margin of error, and hypothesis testing. So let's go ahead and get right into the definitions. Our first definition we're going to be working with here is confidence interval. And I mentioned this in the last video, and it's actually the range of estimates at a specified confidence level, which is usually 95%, but as you'll see in this lesson, it can be others. The way you calculate it is with x bar, so that's our observation value, right? And then we would do plus or minus our margin of error. And sometimes I will write the margin of error as ME. So if you see ME, that means margin of error. And number 11 is margin of error. And so margin of error equals our Z star times S over square root of N. And these are all these definitions I'm giving you are for means. And obviously you will change it for proportions like how we did last time. So it changes just a little bit for proportions and it stays the same. And so our Z star, number 12 is going to be Z star, and that is the amount of standard deviations away from the middle that the confidence level indicates. And so, for example, Z star would be 2 in a 95% confidence interval based on the empirical rule. And I think I misspelled this right here. So that would be empirical rule. And so that's basically saying, right, with 95% confidence interval, that it's 2 standard deviations to the right and 2 standard deviations to the left. So that's why our Z star there is 2. And that just means how far you move each way. And number 13 is the null hypothesis. And that is basically the status quo or the normal. And we would write that with H naught. And number 14 is the alternative hypothesis. And that's what we think is actually happening or what we're testing for. So that would be written with H and then subscript of A for alternative hypothesis. Okay, so let's do it. First problem. A vet collects a random sample of 40 cats that she has treated over the years and indicates the number of years each cat lived. 10 of the 40 cats lived to be over 11 years old. And so now this is basically what we're going to be looking for. So 10 of the 40 were the success, and then 30 of the other 30 would be the failures. So our p hat here, and remember this is proportions, so we're using p hat instead of x bar. So we're using p. And so this would be 0.25, right? Because this equals 10 over 40. And then it asks us to use the empirical rule to construct a 99.7% confidence interval of the proportion, rounded to 3 decimal places, of all cats that will live to be more than 11 years old. And so if you remember, let's see, we have the empirical rule, right, which is the 68, 95, 99.7 rule. And so 99.7% means that we will be 3 standard deviations to the right and the left, right? So this tells us that our Z star equals 3. Okay, and so now we would need to construct the confidence interval, it's p hat plus or minus the margin of error, and this is the same thing as p hat plus or minus Z star times the standard error for a proportion, which is equal to square root of p hat times 1 minus p hat over n. And so now what we would need to do for the rest of this problem is just fill that in. So this would be 0.25 plus or minus 3 times square root of 0.25 times 0.75 over, and what was the n here? N was 40. So this will give us 0.25 plus or minus 0.205. And so this would mean that if you did that, so if you do plus 0.25 plus 0.205, this gives us 0.455. And then if you do 0.25 minus the 0.205, right, because we have to do both of them, so this gives us 0.045, right? And so this is basically what it is to construct a confidence interval. And then we would write our confidence interval like something like this. So it would be 95% conf interval equals 0.045, and then it's going to be a comma, and then we will write 0.455, right? And so that makes sense because the bottom number, or the left part of the confidence interval, would be 0.045 and 0.455 would be the top of the confidence interval. And so when we do a 99.7% confidence interval, that means that we are 99.7% confident that the proportion of all cats will fall in between these two values. And so that's why we use confidence intervals, is because it gives us an estimate of where the actual proportion would fall. All right, so the next part says, what sample size should the vet use to achieve a margin of error of no more than 8% for the 99.7% confidence interval using the empirical rule? And it tells us right here to use p equals 0.5 since we do not know the exact population proportion. So if you remember our margin of error definition, so ME equals Z star times square root P 1 minus P over N. And so since we don't know, I mean, we do know our N here, right? It's because, so our N for this part of the problem was 40. So N equals 40. We're still going to use N equals 40. Actually, no, I apologize. We don't know our N here, and that's what they're asking us to find. I'm sorry. So it says, what sample size should they use? So we were going to use, algebra here to solve for our N in our equation. So what we would do, it says margin of error no more than 8%. So that means 0.08. So 0.08 would be no more than, right? Which means less than or equal to. Actually, no, I'm sorry. That means greater than or equal to, right? Because it's going to be I'm going to write our margin of error on this side. So it would be the Z star. And so since we have the 99.7%, Z star equals 3. And then it tells us to use 0.5 for P. So it would be 0.5 times 0.5 over N, right? And so now we would just need to use algebra to solve for this N. So what we would do is we'd move this 3 over. So it'd be 0.08 over 3 is greater than or equal to square root 0.5 times 0.5 over N. And then next thing we would need to do, we would need to square both sides. And that cancels out our square root, so we'd cancel that out and cancel that out. And then we were just left with 0.08 over 3 squared is greater than or equal to 0.5 times 0.5 over N. Right? And so now the last thing that we need to do is we need to move the N over to the other side, and then we're going to move the 0.08 over 3 squared to the side that the N is on. So how we do that is N over here, we'd multiply by N, and then we divide by the left side. So it would be N is greater than or equal to 0.5 times 0.5 over this whole that whole part on the left, so 0.08 over 3, and that's squared. So this ends up giving us an answer. N is greater than or equal to 352. I didn't write that well, sorry. So 352. And that's how you solve that problem. That problem isn't too difficult. The hardest part of that would be the algebra. Other than that, you know how to do everything else in that part. So, yeah. All right. Next thing says, in 2013, the Pew Research Foundation reported that 45% of U.S. adults report that they live with one or more chronic conditions. However, this value is based on a sample and is therefore only an estimate of the proportion of all U.S. adults who live with one or more chronic conditions. The study reported a standard error of about 1.2%, so SE equals 0.012, and a normal model may be reasonably used in this setting. That's important. So it's normal. Using the empirical rule, calculate a 95% confidence interval for the proportion of U.S. adults who live with one or more chronic conditions and interpret this interval. So X bar, right, this is based on a sample. So our X bar is going to have to be, right here, it's going to be 45%. So X bar, or actually, I'm sorry, we'll be using P hat here because it's a proportion. So P hat equals 0.45, right? And then if you remember, we need to calculate the confidence interval, so that'd be P hat plus or minus Z star times the standard error. And it tells us in this problem the standard error equals 0.012, so we already know that part. And then it's a 95% confidence interval, so that means Z star equals 2. right? Because 95% falls within 2 standard deviations away from the middle. So that tells us z star equals 2. And then all we're left to do here is say 0.45 plus or minus 2 times 0.012. And this gives us a confidence interval of 0.426 and 0.474. All right, there we go. That's a 95% confidence interval. And it also asks us to interpret this interval. And so that's what, so when it says interpret this interval, it's basically asking 95% chance, or 95% confident that between these two values, so 95% confident that the percent of U.S. adults that live with one or more chronic conditions is this. So 95% confident that that is the real proportion of U.S. adults that live with the chronic conditions. All right. So in 2013, the Pew Research Foundation. Okay, so this is the same problem. So yeah, same problem here. And then it just says now we need to identify each of the statements as true or false. So A, we can say with certainty that the confidence level calculated in the previous problem contains the true percentage of U.S. adults who suffer from a chronic illness. So we can't say with certainty. So the thing here is that it says certainty. So that would be 100% certain that the confidence interval contains the true percentage of U.S. adults, right? And we don't know that. We're 95% confident of that. We're not 100% confident. So this would be false. If we repeated this study 1,000 times and constructed a 95% confidence interval for each study, then approximately 950 of those confidence intervals would contain the true fraction of U.S. adults who suffer from chronic illnesses. And yes, that is true because, that's the point of a confidence interval, is that if you did it 1,000 times, the expected value would be 0.95 times 1,000, so 0.95 times 1,000 equals 950. And that's basically what a confidence interval is. All right, C says since the standard error is 1.2%, only 1.2% of people in the study communicated uncertainty about their answer. And that's just false because that's not our definition of standard error. Standard error has nothing to do with the answer of a study. It just has to do with the formula, right? So remember, standard error for this would be P1 minus P over N and then square root of all that, right? So that's not the same thing. That just don't even let that question throw you off. That's just false. Okay, a hospital administrator hoping to improve wait times decides to estimate the average emergency room waiting time at her hospital. She collects a simple random sample of 64 patients and determines the time in minutes between when they checked into the ER until they were first seen by a doctor. A 95% confidence interval based on this sample is 128 to 147, which is based on the normal model for the mean. Determine whether the following statements are true or false. So the first one says the confidence interval is not valid since we do not know if the population distribution of the ER wait times is normal. And so remember our CLT that says N has to be greater than 30, right? So it'd be N is greater than or equal to 30. And then if this one, we see the number, that the N here is 64. So N equals 64, which is obviously greater than or equal to 30. So it doesn't matter what the population distribution is, as long as our N is greater than or equal to 30. So this is false because the confidence interval is valid. So the misstatement there would be is not valid. In B, it says we are 95% confident that the average waiting time of these 64 emergency room patients is between 128 and 147 minutes. So this is also false because we are 100% confident. 100% confident that the average waiting time of these 64 emergency room patients is between these, is right, and that's because we made the confidence interval based on that sample. So we of course know that the average waiting time of those patients is right in the middle, right? Because that would be our X bar, and we would have to add and subtract the margin of error to find the confidence interval. So we know the average waiting time is in the middle. So 100%, not 95%. And now C says we are 95% confident that the average waiting time of all patients at this hospital's emergency room is between 128 and 147 minutes. So this part is actually true, because that's what a confidence interval is it says that 95% confident that the population mean is in the middle of those. Right? And so that's basically just asking if you know the definition of a confidence interval. All right, so part D says a 99% confidence interval would be narrower than the 95% confidence interval, since we need to be more sure of our estimate. So a 99% confidence interval, right? If you think about it, I'm just going to draw a quick normal graph. So let's say a 95% confidence interval is right here. So 95% would be between these two. And then if we need a 99% confidence interval, which means we need more area between our cutoff points, so that would be a 99% would be right there, right? About right there. That's just an estimate. So 99% would be it would be skinny. It would be wider than a 95% confidence interval. So this is false. And then E just says the margin of error is 9.5 and the sample mean is 137.5. And you can test that out by because remember our formula for a confidence interval would be X bar plus or minus the margin of error. So if we did 137.5 plus or minus 9.5, that gives us 128 and 147. So yes, that's true, because that's what our confidence interval was up here, right? So 128 to 147. Boom. Easy. True. All right, the next thing says a 95% confidence interval for mu turns out to be this. Is it correct to say that mu falls between those with a probability of 0.95? And so now this is a pretty good question, because this is just saying, like, this is basically just asking again if you know the definition of a confidence interval. And so it asks, is it correct to say that mu falls between those with probability of 0.95? And this would be true, of course. Or so yes, actually. Right? Because that's the point of a confidence interval. And basically just saying a probability of 0.95 that it falls between those two values, and that is the definition of a confidence interval. All right. This last part, or this second to last part, says a 95% confidence interval for mu turns out to be this. Is the mean mu included in the 95% confidence interval? So remember, our mu is our population statistic, right? And so obviously our X bar would be included in this, but we don't know for sure that the mean is included in this. So I'm going to write perhaps, but not sure, but not certain, right? So we'd be 95% sure that it's included in that confidence interval, but we would be certain that our X bar is included in there, because that's what we make the confidence interval off of. But we don't know for certainty if the population mu is included in that interval. All right, last thing says, the credibility of a noted psychic was being tested to determine if the psychic's abilities are greater than what would happen just by guessing. The psychic was presented with 200 cards face down and was asked to determine if each card was one of 5 symbols: a star, a cross, a circle, a square, or 3 wavy lines. The psychic was correct in 50 guesses. So this basically, or in 50 cases. So what are the hypotheses being tested, right? And so if you remember, we have our null hypothesis, and then we have our alternative hypothesis. And so this is basic. So then we would, for the null hypothesis, we would say it would be by guessing. So it would be P equals 0.2, right? Because we have five symbols, and if you were just guessing, you would get 1 out of every 5 correct, which is equal to 0.2. So our null hypothesis is P equals 0.2. And your null hypothesis, so whenever you have a null, it's always going to have an equal sign there. Always. So if you have a multiple choice question, and then it says, and it's asking you what the hypotheses are, and then it has a null hypothesis without an equal sign, then you know it's wrong immediately, because your null always has to have an equal sign. No matter what it is, it always has to have an equal sign there. And then so our alternative hypothesis would be what we think is actually happening. And so that would be that the psychic is actually not guessing and knows what's happening. So this would be P is greater than 0.2, right? Because that would make them credible and make them better than just guessing. So that's basically what that's asking there. Is that's just an introduction to hypothesis testing and asking you to identify what the hypotheses are in this problem. And that's about all I have for you for this one. So thank you for watching, and I'll be back with the second to last lesson very soon.